These four acceleration components are called the sliding acceleration, normal acceleration, Coriolis acceleration, as well as the tangential acceleration. Bear in your mind you have two velocity components and four acceleration components in the polar coordinate. Polar coordinate is very useful to analyze both constrained and unconstrained motion. In this case, we have a mass C which can rotate as well as sliding at the same time. The mass C is allowed to slide in the arm AB. A spring is connected to the mass C to constrain its motion. The distance between C and B are given R, and then the arm AB is rotated with angular velocity omega. The mass C is experiencing the curvilinear motion, therefore we can use the polar coordinate. We let the B to be the origin, and the direction from B to C is the radial direction, ER. 90 degrees away from the radial direction, you have the transverse direction, E theta. If the angular velocity changes the direction, your transverse direction will change to this. With that, we can obtain the displacement vector, which is equal to the R magnitude here, multiplied with the radial direction, which is ER. Next, we can find the velocity vector by using this formula. First of all, you have the radial velocity in the radial direction here, R dot. This velocity is also called the sliding velocity because the mass C is moving towards A and the radius changes with respect to time. If the mass C is not allowed to slide along the AB arm here, then the radial velocity of the mass C will be equal to 0. The transverse velocity can be found in the transverse direction here and is equal to the R multiplied with the theta dot. Theta dot is the change of the angle with respect to time, and is also equal to the R multiplied with the angular velocity. When the arm stops rotating here, your angular velocity will be equal to 0. Then in this case, the transverse velocity will be equal to 0, because when you substitute omega 0, multiply, you obtain your V theta equal to 0. In some books, the transverse velocity is also known as the tangential velocity. You need to be careful that its direction may not tangent to the path. For example, over here, this is your path in the orange color, and your transverse velocity is not tangent to it. The velocity that tangent to the path is this velocity, which is the resultant velocity. The transverse velocity here can be tangent to the path when this radial velocity equal to 0. So in this case, the resultant velocity will be equal to the transverse velocity and is tangent to the path. This is the acceleration formula, and we can separate the acceleration component into four parts. In the radial direction, you have the sliding acceleration and the normal acceleration. Sliding acceleration can be obtained by differentiate the sliding velocity. You can use the R double dot or d square R over dt square to compute the sliding acceleration. The sliding acceleration of mass C will cause the mass C to slide and then move toward the point A here. If the mass C here is not allowed to slide, then the radius will be constant. So in this case, the sliding velocity and the sliding acceleration will be equal to 0. If the mass C here has a constant radius or the sliding velocity, then since R dot is constant, the change of R dot with respect to time, which is the sliding acceleration, will be equal to 0 as well. The normal acceleration is in negative, therefore is opposite to the radial direction. This acceleration is always pointing toward the center or the origin that we select. The normal acceleration is well known as the centripetal acceleration, and the equation is equal to negative R omega squared. If you success to compute the transverse velocity by using the previous equation, where your V theta equal to R omega, so we can obtain the normal acceleration to be negative transverse velocity squared divided by R. When you substitute the transverse velocity inside this formula, So you obtain negative r square omega square divided by r. The r here can be cancelled, then you obtain negative r omega square. With that, we prove that this term is equal to this. So these are the two accelerations in the radial direction. You must know the normal acceleration always add toward the center, and the sliding acceleration here always add outward from the center. We have the tangential acceleration and the Coriolis acceleration in the transverse direction. You can find the tangential acceleration by using the formula r theta double dot. Theta double dot is equal to the d square theta divided by dt square, and is also called the angular acceleration. If the mass c does not rotate with the angular velocity, or it rotates with constant angular velocity, you will obtain zero angular acceleration. So, if there is no rotation or constant angular velocity, then the tangential acceleration will be equal to 0. The direction for the tangential acceleration is always 90 degrees to the radial direction. You need to be careful that its direction is not necessarily tangent to the path. For example, over here, this is your path in the orange color, and this is the transverse direction. The tangential acceleration here is not necessarily tangent to the path here. You need to be careful with the term. If you use the tangential acceleration in the normal tangential coordinate, the tangential acceleration is always tangent to the path in the normal tangential coordinate. Lastly, you have the Coriolis acceleration, which is equal to 2 multiplied with the r dot theta dot. So this acceleration is not easy to be visualized like others acceleration because it is contributed by two elements. One from the constant change in terms of the radial direction. Another element is due to the constant change in terms of the transverse velocity. In simple, to experience the Coriolis acceleration, the object must experience sliding velocity, where the object is allowed to slide, and the r can be changed. At the same time, the object must experience rotation, which is the angular velocity. So if the object is slide, at the same time rotate with angular velocity, then we are saying the object is experiencing Coriolis acceleration. So this is the four acceleration components that we obtain in the polar coordinate. Let's consider a special case where we let the r to be constant. In this case, the particle will undergo the circular motion. Since radius is constant, r dot and r double dot will be equal to 0. And then this component, which is the sliding acceleration, will be equal to 0, and the Coriolis acceleration will be equal to 0 as well. And also your sliding velocity will be equal to 0. In the circular motion here, you only have the tangential velocity r omega, which is in this direction. For the acceleration, you have the tangential acceleration r alpha in the transverse direction here. And you have the normal acceleration, or what we call the centripetal acceleration, which is acting toward the center here. The centripetal acceleration can be found by using these two formulas. So for the first formula, you can find it by using negative r omega square. You can also find the centripetal acceleration by taking negative tangential velocity square divided by radius. So if you constrain the motion to the circular motion only, then you no longer have the sliding acceleration and the Coriolis acceleration. You only have the normal acceleration and the tangential acceleration. This result is similar to the one that you obtain by using the normal tangential coordinate. You must know the difference between the centripetal and centrifugal acceleration. In this example, we have a ball moving in the circular motion. At a particular moment, the ball is located here. The ball is experiencing two accelerations. One is the normal acceleration, which is acting towards the center, and it can be found by using the negative r omega square. This normal acceleration is also called the centripetal acceleration. Centripetal means that it is center seeking, therefore this acceleration is always pointing to the center. In this question, you are going to predict the direction of the ball move after you cut the string here. Some people might think when the string is broken and the yellow ball will move in this direction. This is because they imagine there is a centrifugal force pushing in this direction, which causes the ball to accelerate with the centrifugal acceleration. Some might think that when the string is broken, there are two accelerations acting on the ball. One is from the tangential acceleration, another is centrifugal acceleration. So they predict the ball will move in the resultant acceleration direction here. So what do you think? You think the first case is correct or the second case here? In fact, the centrifugal force is not a real force, and what we say is a fictitious force. It should not exist in the inertial frame, therefore these two predictions is wrong. In actual scenario, there is no such centrifugal force push the thing in this direction. So you should know that the centrifugal acceleration is fictitious and is not an actual acceleration and doesn't exist in the inertial frame. In actual, there is no so-called centrifugal force that is pushing on the object, it's just the inertial effect. For example, imagine that you are inside a bus that is moved with 50 km per hour. So you and the ball inside the bus is also moving with the 50 km per hour. How if the bus suddenly stops? So if the bus suddenly stops, it will become 0 here. However, you and the ball inside the bus is moving with 50 km per hour previously. So your inertia tends to remain its original speed. So if there is a guy in an inertial frame watching this activity, it seems the bus is stopped and then the ball and the man inside move forward. You should know that there is no force pushing you forward. The pushing force is not real, it's only a fictitious force, which is due to your inertia. Let's look back our example. So in this case, you should know that the centripetal acceleration is always true. When you hold the ball here, before you cut the string, the centripetal force is the pulling force from you to hold the string when the ball is rotating in a circular motion. So once you cut the string is broken and the pulling force to hold the string is gone. Therefore, you obtain 0 centripetal acceleration. So the remaining acceleration is only the tangential acceleration. Therefore, the object will move in this direction. In this example, you have the ball rotate in the clockwise and you hold the ball to rotate in the circular motion using the casing. Predict the movement of the ball if you release in the position 1 and the position 2 here. If the centrifugal force is true and is exists, then the ball at the position 1 will move in this direction, and in this direction if it is released in the position 2. So these two directions is outward from the center. On the other hand, centripetal acceleration is the acceleration AN, which is pointing toward the center in these two cases. And you have the tangential acceleration, which is 90 degrees to the centripetal acceleration. When you release the ball, you remove this casing. In this case, the centripetal acceleration will be equal to 0. Then the remaining acceleration is the tangential acceleration. So if the centrifugal force does not exist, then the ball will move in the tangential direction after you release it. Watch the video and check which one is true. So for the first case, when you release in this point, you can see it's moving in the tangential direction. So for the second case, it also follows the same. So the results show that it moved in the tangential direction as we predicted, and the centrifugal acceleration is not exist because it is fictitious. You should know what is the Coriolis effect. Previously, you learned about the Coriolis acceleration, which is equal to 2 multiplied with the sliding velocity multiplied with the angular velocity. So the Coriolis force is a fictitious force. Same like the centrifugal force, this Coriolis force is not an actual force. You can visualize the Coriolis force in the non-inertial frame, such as the rotating frame. In this example, you have platform which is rotated in clockwise direction. Imagine that you throw this ball from the center to the outward. The ball is moved with the sliding velocity. At the same time, it experiences the angular velocity. Then the Coriolis acceleration will not equal to 0. And we will see the Coriolis effect acting on the ball when we are in the rotating frame. So you have two guys here. One guy is the yellow guy, which is watching the motion from an inertial frame. So you see the ball is moving in the straight line when you are in the inertial frame. Another red guy here is watching the motion from the rotation frame, and you see a curve. From the top view, the red guy initially is at this position. When the ball is thrown to him, the position of the red guy changes with the rotating frame. This red guy thought there is a force caused the ball to move in curve, which is known as the Coriolis force. In actual, the Coriolis force is fictitious and therefore is not exists in the inertial frame here. If you are the yellow guy who is in the inertial frame, then you see the ball move in a straight line, and there is no Coriolis force that makes the motion to be curved here. The Coriolis effect can be found in the rotating frame, that you assume there is a fictitious force, which is the Coriolis force, that causes the ball to move in curve. Let's look at this video. The camera is fixed at ground, which is an inertial frame, because it's not moving. You can see there are two guys sitting in the rotating platform and throw the ball to each other. They try to throw the ball in a straight line. However, the partner cannot catch the ball easily. So why does this happen? Let's try to mount the camera at the rotating frame, which is the non-inertial frame, and see what happens. So you see this guy is throwing the ball, and the ball is not moving in a straight line, but is moving in a curvilinear line. In a rotating frame, to throw the ball exactly to the partner here, you must consider the Coriolis effect. This is because the ball is experiencing the Coriolis acceleration, which makes it move in a curve. If you are the guy who threw the ball in the rotating frame, you see the ball move in curve, although you throw it in a straight line. The curve motion is due to the Coriolis effect. It can be seen only if the observer in the rotating frame. When the observer is in the inertial frame like this case, the Coriolis effect does not exist, and you see the ball is just moving in a straight line. In summary, we cannot find the Coriolis effect in the inertial frame. This is because the Coriolis force is fictitious and it does not exist in actual. We can see it only in the rotating frame.